This presentation is about precision as a goal for data collection. My name is John Kreschke, and this talk was given at the University of California at Irvine on March 14, 2014. For many scientists, happiness is rejecting a null value. It's the main goal of research, especially in the psychological sciences. But there are some unhappy consequences. In particular, rejecting the null can be done with a tiny effect size. In this graph, we see some normally distributed data. P is far less than 0.05. It's down at 0.002. We've rejected the null. But look, the effect size is tiny. So what we really want is an estimate of the parameter value. How big is the effect? And rejecting the null can be done with extremely poor precision. Here's a very small data set with an n of only 7. P is less than 0.05. It rejects the null, but the estimate of the underlying parameter, the underlying mean, is very wide. What we really want is the precision of the estimate of the parameter value. Here's a quote from Jacob Cohen. "Yet, confidence intervals are rarely to be found in the literature. I suspect that the main reason they are not reported is that they are so embarrassingly large. But their sheer size should move us toward improving our measurement by seeking to reduce the unreliable and invalid part of the variance in our measures." The frequentist psychologist's response is the new statistics. The flagship journal of the Association for Psychological Science is the journal Psychological Science. Here's an excerpt from their latest editorial, which says that they now recommend the use of the new statistics, effect sizes, confidence intervals, and meta-analysis to avoid problems associated with null hypothesis significance testing. While I admire the goals, I eschew the methods. The new statistics is already obsolete. It's superseded by Bayesian methods. Rejecting the null also suffers from Meehl's paradox. This is named after Paul Meehl. He was the president of the American Psychological Association in 1962. He was famous for his hard critiques of soft psychology. In particular, one of his articles was called Theory Testing in Psychology and Physics, a Methodological Paradox. Here's Meehl's paradox. First, theories should be more difficult to confirm as measurement precision increases, because small discrepancies from prediction will be revealed. The premise here is that all theories are wrong. There's always some discrepancy between the theory and reality, and as you get more precision, you should be able to detect that discrepancy. Now, consider a theoretical prediction posed as a non-null, which can be confirmed by any non-null result. In most research, the null cannot be literally exactly true. So from premises 2 and 3, confirming a non-null prediction, that is rejecting the null, gets easier as precision increases. And that contradicts premise 1, which says that theory should be more difficult to confirm, not less difficult as precision increases. A solution to Meehl's paradox was offered by Serlin and Lapsley. They said we should strive to accept a predicted value, not to reject a not predicted null value. This implies a need for a high precision estimate with what they called a good enough belt, or what I call a region of practical equivalence, around the predicted value. The frequentist approach to this is called equivalence testing, and it uses confidence intervals. A Bayesian approach overcomes problems with confidence intervals, as we'll describe later. Now, how precise an estimate is needed? That depends on current measurement capabilities and competing theories. Quote, admittedly, specifying the rope limits is difficult. The width of the rope depends on the state of the art of the theory and of the best measuring device available. It depends on the state of the art of the theory because a historical look at one's research program or an examination of a competing research program will help determine how accurately one's theory should predict in order that it be competitive with other theories. This sort of thing is routinely done in clinical equivalence testing, or what's sometimes called non-inferiority testing, where they look at existing effects and they're trying to see if novel approaches, novel drugs, are equivalent or non-inferior to existing effects. And this requires theories to declare an effect size. There's no free lunch where you can just reject anything non-null. You have to carefully consider what effect size you want to confirm. Now, rejecting the null is ancillary in many fields of science. Here's a quote from a recent comment on my blog. In my own field, wildlife ecology, we can rarely do experiments, so hypothesis testing is scarcely relevant anyway. The focus is on estimation of density, of abundance, occupancy, survival, etc., or on modeling. Now, what's wrong with using frequentist confidence intervals? Well, confidence intervals are as fickle as p-values. They're sensitive to sampling and testing intentions, and that's because confidence intervals are defined in terms of p-values. And there's no distributional information. Values in the middle of a confidence interval cannot be said to be more credible than values at the limits of the interval. The following slides explain the above points. You can also see some pages in this article shown here. Now, what is a p-value? The p-value is the probability that the actual sample statistic, such as the sample t, or a result more extreme, would be obtained from the null hypothesis if the intended sampling and testing were repeated ad infinitum. I'll try to illustrate that with this cloud of possibilities. Here in the lower left, we see the analyst thinking up the null hypothesis and imagining what would happen if you were to generate random data from the null hypothesis. Typically, every random data set is thought to have this fixed sample size n indicated between the hands. That's the fixed size. The cloud is the space of possible outcomes from the null hypothesis for stopping at size n. The actual outcome is shown by the red brick. It's the concrete number that's fixed by observation. And the p-value is the proportion of that cloud of possibility that's more extreme than the actual outcome. As the title of this slide says, the p-value depends on the intended stopping rule. Here, the cloud is determined by stopping at size n. But here, we're generating this cloud of counterfactual possibilities by considering stopping at time t. We're going to collect data until 5 o'clock on Friday afternoon. So every sample has a fixed duration of collection, but different samples could have different sizes. Because of this cloud of possibilities is different, and the p-value is different. The actual outcome is the same as before, but we're comparing it to a different cloud of counterfactual possibilities, so the p-value is different when we have changed the stopping rule. The p-value also depends on the intended tests. Here's the space of possible outcomes from the null hypothesis for doing one comparison. Say you've got two groups and you're comparing this one group against the other. But if you're comparing those two groups in the context of making other comparisons with other groups, even though the data in those two groups don't change, if you're making several comparisons, you can now get apparent differences from other comparisons that enlarge the space of counterfactual possibilities, and the p-value has grown. So the p-value depends on the intended tests. So what does this mean for confidence intervals? Well, let's consider the general definition of a confidence interval. The 95% confidence interval is the range of parameter values, such as the difference of means, that would not be rejected by p less than 0.05. Hence, the 95% confidence interval is as ill-defined as the p-value. We see this dramatically in confidence intervals corrected for multiple comparisons. Confidence intervals also provide no distributional information. Here's a picture of a confidence interval on the difference of means. We want to see a distribution on that interval, but no matter how hard we look, it's really just not there. The value in the middle of the confidence interval is not more credible than the value at the limit of the confidence interval. And the range of the 95% confidence interval does not span the 95% most credible values. Well, the above are qualitatively true, but only by virtue of their approximate relation to Bayesian estimation, not by the actual meaning of the confidence interval. So I'd like to tell you briefly about Bayesian parameter estimation. I'm going to show you a quick example of Bayesian data analysis, and the key point is that precision may be measured as a highest density interval. Here's an example of robust Bayesian estimation for comparing two groups. Consider two groups where we're measuring the intelligence quotient, the IQ, of a smart drug group and of a control group. The top right histogram shows the data for the placebo group, and the bottom right histogram shows the data from the smart drug group. Now, if you look closely, you can see there are some outliers, some data values pretty extreme, but as far as we know, these are representative of the two groups, so we cannot just arbitrarily exclude them from the analysis. The data from each group are described by t-distributions, highlighted in yellow, using 5 parameters altogether. Each group has a mean parameter, mu, a sigma parameter, which describes the width of the data, and there's a parameter nu, which controls the heaviness of the tails. These tails accommodate the outliers. In a Bayesian analysis, we have to establish prior credibility on the parameters. What do we know about these parameters before the new data? For the purpose of this analysis, we're going to have a very non-committal, vague prior, which is simply broad on the scale of the data. The only information we're using is the approximate scale of the data. Are we measuring IQ scores? Are we measuring length on nanometers or distance in light years? So there's one fixed data set shown as these red histograms. What we do in a Bayesian analysis is now reallocate credibility across parameter values so that now the credibility is consistent with the data. Here's the posterior distribution on the parameter values. These are parameter values from the posterior distribution, a huge number of combinations of those 5 parameters that are jointly credible given the data. These blue distributions are not data distributions, and they're not sampling distributions from a null hypothesis. These are distributions of credible parameter values given the data. Please proceed to part 2 at this time.